The sky above us has always carried something more than light. It has carried time itself, frozen in the act of crossing distances we can barely name. For as long as humans have looked upward, we have tried to measure what we see, to place boundaries around the vastness pressing down on us from every direction. But measurement requires reference points, and the universe does not offer them freely. It offers only light, delivered across gulfs so immense that the very act of seeing becomes an act of looking backward through history. When we observe distant objects, we're not seeing them as they are, but as they were sometimes billions of years before our planet even existed. This fundamental delay, this cosmic time lag, is not a limitation of our instruments, but a consequence of the structure of reality itself. Light moves at a fixed speed, and space is unimaginably large. The combination of these two facts means that every observation is also an archaeology, every image a fossil of a moment that has already passed beyond retrieval. If you're watching this now, consider expanding your view to full screen. Let the scale of what we are discussing fill your vision the way it fills the actual universe. And if this exploration resonates with you, subscribing ensures you will continue to receive investigations like this one, where we do not simplify or condense, but instead commit fully to the depth and strangeness of what science has revealed. These are not brief explanations. They are immersions. The James Webb Space Telescope is not merely a successor to earlier instruments. It is a reconstruction of how we gather information from the universe. Its mirror, composed of 18 hexagonal segments coated in gold, spans more than 6 meters across. Gold was chosen not for appearance, but for its reflectivity in the infrared spectrum, the range of light that carries information from the earliest and most distant objects in existence. Infrared light can penetrate dust clouds that block visible wavelengths. It can reveal heat signatures from objects too cold or too far to glow in visible light. And most crucially, it can capture light that has been stretched by the expansion of space itself. Light that left its source as ultraviolet or visible radiation, but has been pulled across the spectrum into the infrared by the time it reaches us. This stretching, known as redshift, is not a distortion, but a direct measurement of cosmic expansion. The more stretched the light, the farther it has traveled, and the earlier in cosmic history it originated. Webb orbits the Sun at a point called Lagrange 2, roughly 1.5 million kilometers from Earth in the direction opposite the Sun. This position, gravitationally balanced between Earth and Sun, allows the telescope to remain in a stable orientation with its sun shield always blocking the heat and light of both Earth and Sun simultaneously. The sun shield itself is a structure of 5 layers, each thinner than a human hair, separated by gaps that allow heat to radiate away into space. The difference in temperature between the sunlit side and the shaded side exceeds 200 degrees Celsius. This extreme thermal isolation is necessary because infrared observations require the instruments themselves to be cold. Heat is infrared radiation, and a warm telescope would blind itself with its own glow. Webb's instruments operate at temperatures barely above absolute zero, maintained by passive radiative cooling and, in some cases, mechanical cryocoolers that further suppress residual warmth. The scale of a universe is not a single number. It is a cascading series of revelations, each one redefining what came before. When we say the universe is large, we are compressing an almost infinite variety of distances into a single inadequate word. The distance from Earth to the Moon is roughly 380,000 kilometers. The distance from Earth to the Sun is 150 million kilometers, a span we call an astronomical unit. The nearest star beyond our Sun, Proxima Centauri, lies 4.2 light-years away, meaning light itself takes more than 4 years to cross that gap. A light-year is not a measure of time, but of distance. The length light travels in 1 year, approximately 9.5 trillion kilometers. Already we have crossed thresholds where human intuition falters. We can say the numbers, but we cannot picture them. Our minds evolved to navigate environments measured in meters and kilometers, not trillions. Our galaxy, the Milky Way, spans roughly 100,000 light-years from edge to edge. It contains between 200 and 400 billion stars, many of them accompanied by planets, some of which likely harbor conditions suitable for life. The Milky Way is not unique. It is one galaxy among hundreds of billions in the observable universe, possibly more. Each of those galaxies contains billions or trillions of stars. The observable universe, the region from which light has had time to reach us since the beginning, extends approximately 46 billion light-years in every direction. This figure is larger than the age of the universe multiplied by the speed of light, because space itself has been expanding during the time light has been traveling. Objects that emitted light 13 billion years ago are now much farther away than 13 billion light-years, carried outward by the stretching of space itself. Before Webb, our deepest images of the universe came from the Hubble Space Telescope, which observed primarily in visible and ultraviolet wavelengths. Hubble's deep field images, produced by pointing the telescope at a seemingly empty patch of sky and exposing the sensor for days, revealed thousands of galaxies in regions previously thought to contain nothing. These images shocked astronomers not only with the number of galaxies, but with their variety. Galaxies appeared in every stage of development, from chaotic irregular clumps to mature spirals and ellipticals. They existed at distances corresponding to light travel times exceeding 13 billion years, meaning we were seeing them as they appeared less than a billion years after the Big Bang. But Hubble's vision had limits. The earliest galaxies, those forming in the first few hundred million years, were invisible to it. Their light had been redshifted beyond the range Hubble could detect. Webb was designed specifically to pierce that veil. Its infrared sensitivity allows it to detect galaxies that formed when the universe was only a few hundred million years old, during an era astronomers call the Cosmic Dawn. These galaxies are not merely distant. They are ancient snapshots of a universe in its infancy, when the first stars ignited and the first heavy elements began to form. Hydrogen and helium, the simplest elements, were produced in the Big Bang itself. Everything heavier, carbon, oxygen, nitrogen, iron, gold, was forged inside stars or during their explosive deaths. The first stars contained no heavy elements at all. They were composed almost entirely of hydrogen and helium, and their formation marked the transition from a dark universe filled with neutral gas to a luminous one filled with ionizing radiation. Understanding the true scale of the universe requires more than measuring distances. It requires understanding the history embedded in those distances. Light from a galaxy 10 billion light-years away carries information about the universe as it existed 10 billion years ago. That galaxy has continued to evolve during the time its light has been traveling toward us. Stars have formed and died. Elements have been synthesized and dispersed. The galaxy may have merged with others, changing its shape entirely. The image we receive is not a portrait of the galaxy as it is now, but as it was. Cosmology is therefore inherently historical. We cannot observe the present state of the distant universe. We can only observe its past. This creates a paradox of knowledge. The farther we look, the more we see of the universe's youth, but the less we see of its present state. The closest galaxies show us the universe as it was millions of years ago, a negligible delay on cosmic timescales. The farthest galaxies show us the universe as it was billions of years ago, a span that encompasses the majority of cosmic history. But we cannot see those distant galaxies as they exist today. We cannot know whether they have survived, merged, or been torn apart. We are archaeologists examining fossils, not biologists studying living organisms. Webb's first deep field image, released in 2022, covered a patch of sky roughly the size of a grain of sand held at arm's length. Within that minuscule region, thousands of galaxies appeared, many of them never seen before. Some were familiar spirals and ellipticals, their light slightly reddened by distance. Others were irregular smudges, their structures still forming. And some were tiny red dots, barely resolved. Their light stretched so far into the infrared that they appeared more as spectral signatures than as visible objects. These red dots represented some of the earliest galaxies ever detected, their light having traveled for more than 13 billion years. They existed when the universe was less than 5% of its current age. The expansion of the universe is not an explosion outward from a single point into pre-existing space. Space itself is expanding, carrying galaxies along with it. This expansion was discovered in the 1920s when astronomer Edwin Hubble observed that distant galaxies exhibited redshifts proportional to their distances. The farther a galaxy, the faster it appeared to be receding. This relationship, now called Hubble's law, implied that the universe was not static but dynamic, either expanding or contracting. Combined with Einstein's equations of general relativity, which predicted an unstable universe unless modified by an ad hoc cosmological constant, Hubble's observations confirmed that the universe was expanding. Running this expansion backward in time led to the conclusion that the universe must have been smaller, denser, and hotter in the past, converging toward an initial state of nearly infinite density and temperature. This initial state, colloquially called the Big Bang, marked the beginning of space and time as we understand them. The term Big Bang is misleading. It suggests an explosion, an event that occurred at a specific location in space. But the Big Bang was not an explosion in space. It was an expansion of space itself. There was no pre-existing void into which matter erupted. Space and time emerge together, and every point in space has an equal claim to being the origin. When we look outward in any direction, we're looking back toward the conditions that existed everywhere during the early universe. The distant galaxies we observe are not remnants scattered from central explosion. They are regions of space that have been carried apart by the expansion, their light taking billions of years to traverse the growing distances between us. Measuring cosmic distances is one of the most difficult challenges in astronomy. For nearby stars, astronomers use parallax, the apparent shift in a star's position as Earth orbits the Sun. By measuring this shift, they can calculate the star's distance using simple trigonometry. But parallax only works for stars within a few thousand light years. Beyond that, the shifts become too small to measure accurately. For greater distances, astronomers rely on standard candles, objects whose intrinsic brightness is known. By comparing the known brightness with the observed brightness, they can calculate distance. Certain types of variable stars, such as Cepheid variables, have a relationship between their pulsation period and their luminosity. Measure the period, and you know the luminosity. Compare that with the observed brightness, and you have the distance. For galaxies beyond the reach of Cepheid observations, astronomers use supernovae, specifically type I supernovae, which occur when a white dwarf star accretes matter from a companion and reaches a critical mass, triggering a thermonuclear explosion. Because this critical mass is always the same, type I supernovae always reach approximately the same peak brightness. They are extraordinarily luminous, briefly outshining entire galaxies, and they can be seen across billions of light years. By observing type I supernovae in distant galaxies and measuring their redshifts, astronomers constructed a distance-redshift relationship that revealed something unexpected. The expansion of the universe is not slowing down. It is accelerating. This acceleration was discovered in the late 1990s by two independent teams studying distant supernovae. They found that supernovae at high redshifts were dimmer than expected, implying they were farther away than predictions based on a decelerating universe would suggest. The only way to explain this was to introduce a new component to the universe's energy budget, something that exerted a repulsive gravitational effect, counteracting the attractive pull of matter and driving the expansion to accelerate. This component was dubbed dark energy, and it now appears to constitute roughly 68% of the total energy content of the universe. Its nature remains unknown. It does not clump like matter. It does not interact with light. It appears to be a property of space itself, a kind of intrinsic energy density that remains constant even as space expands. As the universe grows, the total amount of dark energy increases because there is more space, and this increasing dark energy drives the acceleration. Dark energy is not the only invisible component. Observations of galaxy rotation curves, the speed at which stars orbit the centers of galaxies, revealed another mystery. Stars farther from galactic centers were moving faster than expected based on the visible mass. According to Newtonian gravity, stars at the edges of galaxies should orbit more slowly, just as planets farther from the Sun orbit more slowly. But they did not. They maintained high speeds, implying the presence of additional unseen mass. This unseen mass, called dark matter, does not emit, absorb, or reflect light. It interacts only through gravity. It forms halos around galaxies, extending far beyond the visible stars, and its gravitational pull holds galaxies together. Dark matter constitutes roughly 27% of the universe's energy content. Ordinary matter, the stuff of stars, planets, and living things, account for less than 5%. The universe is therefore dominated by components we cannot see directly. We infer their existence only through their gravitational effects. Dark matter through the motion of stars and galaxies. Dark energy through the acceleration of cosmic expansion. These discoveries have transformed our understanding of the universe's structure and fate. Without dark matter, galaxies would not have formed. The slight density fluctuations in the early universe would not have grown into the cosmic web of filaments and voids we observe today. Without dark energy, the expansion might have slowed enough for gravity to eventually reverse it, leading to a big crunch. With dark energy, the universe will expand forever, growing colder and darker as galaxies recede beyond each other's cosmic horizons. Webb is uniquely positioned to study both the earliest galaxies and the processes that shaped them. Its sensitivity to infrared light allows it to detect faint, distant objects that would be invisible to other telescopes. Its spectroscopic instruments can split light into its component wavelengths, revealing the chemical composition, temperature, motion, and redshift of observed objects. By analyzing the spectra of distant galaxies, astronomers can determine what elements they contain, how fast they are forming stars, and how far away they are. This information is critical for understanding how galaxies evolved from the simple, irregular structures of the early universe to the diverse, mature galaxies we see today. One of Webb's key discoveries has been the detection of galaxies at redshifts exceeding 13, corresponding to times less than 300 million years after the Big Bang. These galaxies are surprisingly bright and structured, challenging theoretical models that predicted the first galaxies would be small and faint. Some of these early galaxies appear to contain supermassive black holes, objects with masses millions or billions of times that of the Sun, located at the galaxy centers. The existence of such massive black holes so early in cosmic history poses a problem. Theoretical models struggle to explain how black holes could grow so large in such a short time. Black holes grow by accreting matter, but accretion is a relatively slow process, limited by the rate at which matter can fall inward without being blown away by the radiation produced. Growing a black hole from stellar mass to supermassive scale in a few 100 million years requires near-continuous accretion at the maximum possible rate, a scenario considered unlikely. Yet the observations are clear. These black holes exist. The existence of early supermassive black holes suggests that our models of black hole formation and growth are incomplete. Perhaps black holes in the early universe formed through mechanisms unavailable today. Perhaps they began as much more massive seeds, formed directly from the collapse of massive gas clouds rather than from the remnants of stars. Or perhaps accretion in the early universe was more efficient than current models allow, enabled by different gas dynamics or lower metallicity environments. Webb's observations are forcing theorists to reconsider assumptions that have guided cosmology for decades. Another puzzle involves the rate of star formation in early galaxies. Webb has detected galaxies forming stars at prodigious rates, producing hundreds or even thousands of solar masses per year. This is far higher than the star formation rates in typical galaxies today, which range from 1 to 10 solar masses per year. The early universe appears to have been a far more violent and active place, with galaxies growing rapidly and stars igniting in vast bursts. Why this was the case remains unclear. The gas in early galaxies had lower metallicity, meaning it contained fewer heavy elements, which might have made it easier for gas clouds to collapse and form stars. The universe was also denser, and collisions between galaxies were more frequent, triggering starbursts. But these explanations are incomplete. The details of how gas cooled, collapsed, and fragmented into stars in the early universe are still being worked out. Understanding star formation is critical to understanding the chemical evolution of the universe. Stars are the factories where heavy elements are created. Hydrogen and helium, synthesized in the Big Bang, are fused into heavier elements inside stellar cores. When massive stars exhaust their nuclear fuel, they explode as supernovae, dispersing these newly created elements into the surrounding gas. Subsequent generations of stars incorporate these elements, gradually enriching the interstellar medium. The Sun, for example, contains about 2% heavy elements by mass, inherited from previous generations of stars that lived and died before the solar system formed. The first stars contained essentially no heavy elements. They were pure hydrogen and helium, and their explosions seeded the universe with the first carbon, oxygen, and iron. Webb's infrared vision allows it to study star formation in detail, even in regions obscured by dust. Dust, composed of tiny grains of silicates, carbon, and ice, absorbs visible light and re-emits it as infrared radiation. This makes dusty regions opaque to optical telescopes, but transparent to infrared instruments. Many of the most active star-forming regions in the universe are shrouded in dust, hidden from view at visible wavelengths. Webb can peer through this dust, revealing the young stars within and the processes that govern their birth. The scale of star-forming regions varies immensely. Some stars form in isolation or in small groups, condensing from relatively quiescent clouds of gas. Others form in massive clusters, where thousands of stars ignite within a few million years, their combined radiation and stellar winds sculpting the surrounding gas into vast bubbles and pillars. The Carina Nebula, a star-forming region in our own galaxy roughly 7,500 light-years away, is one such environment. Webb's images of the Carina Nebula reveal towering columns of gas and dust, their edges illuminated and eroded by the intense radiation from nearby young stars. Within these columns, new stars are forming, still embedded in the cocoons of gas from which they condensed. These images are not merely beautiful. They are scientific documents, encoding information about the temperature, density, composition, and motion of the gas, information that can be extracted through careful analysis. The process by which a cloud of gas collapses to form a star is governed by gravity, pressure, and magnetic fields. Gravity pulls the gas inward. Pressure resists this collapse, especially if the gas is warm. Magnetic fields thread through the gas, providing additional support and influencing the geometry of the collapse. For a cloud to collapse, gravity must overcome these resistive forces. This typically requires the cloud to be cold and dense. Cold gas has less thermal pressure, and dense gas has stronger self-gravity. Once collapse begins, the cloud fragments into smaller clumps, each of which may itself collapse to form a star. This fragmentation is why stars often form in clusters rather than individually. The initial cloud breaks apart into many pieces, and each piece becomes a star. As a collapsing cloud contracts, it heats up. Gravitational potential energy is converted into thermal energy, raising the temperature of the gas. Eventually, the core becomes hot and dense enough for nuclear fusion to ignite. Hydrogen nuclei, protons, overcome their mutual electromagnetic repulsion and fuse to form helium, releasing energy in the process. This energy generates radiation pressure that halts the collapse, and the star reaches a stable equilibrium called the main sequence, where it will spend the majority of its life. The time a star spends on the main sequence depends on its mass. Massive stars burn their fuel quickly and live only a few million years. Low-mass stars burn slowly and can live for trillions of years, far longer than the current age of the universe. The most massive stars, those exceeding about 8 solar masses, end their lives in supernova explosions. When such a star exhausts its nuclear fuel, its core collapses catastrophically, and the outer layers rebound in a shock wave that tears the star apart. The explosion releases as much energy in a few seconds as the Sun will emit over its entire 10 billion-year lifetime. The core, if it survives, becomes either a neutron star or a black hole, depending on its mass. Neutron stars are extraordinarily dense objects, with masses comparable to the Sun compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh billions of tons on Earth. Black holes are even more extreme. They are regions where gravity is so strong that not even light can escape. Their boundaries, called event horizons, mark the point of no return. Anything crossing the event horizon is lost forever, at least as far as external observers are concerned. Black holes come in different sizes. Stellar mass black holes, formed from supernova remnants, have masses ranging from a few to a few dozen solar masses. Supermassive black holes, found at the centers of galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, with masses in between, have been harder to detect but are thought to exist. The mechanisms by which supermassive black holes form remain uncertain. They are far too massive to have formed from individual supernovae. They may have formed from the direct collapse of massive gas clouds in the early universe, or they may have grown through mergers, gradually accumulating mass as smaller black holes coalesced. Webb's observations of early supermassive black holes provide critical data for testing these theories. The centers of galaxies are dynamic environments. The supermassive black hole at the center of the Milky Way, called Sagittarius A*, has a mass of about 4 million solar masses. It is relatively quiet, accreting little material and producing only modest radiation. But many galaxies host active galactic nuclei, or AGN, where the central black hole is actively accreting matter from a surrounding disk. As matter spirals inward, it heats up through friction and compression, reaching temperatures of millions of degrees and emitting intense radiation across the electromagnetic spectrum. Some AGN produce jets, narrow beams of particles and radiation that shoot outward from the black hole's poles at speeds approaching the speed of light. These jets can extend for hundreds of thousands or even millions of light years, far beyond the host galaxy. They deposit enormous amounts of energy into the surrounding intergalactic medium, influencing the formation and evolution of galaxies across vast regions of space. The energy output of an AGN can exceed that of all the stars in its host galaxy combined. This radiation heats and ionizes the surrounding gas, suppressing star formation and altering the galaxy's evolution. This process, called AGN feedback, is thought to be a key regulator of galaxy growth. Without it, galaxies would continue forming stars at high rates, converting all their gas into stars and becoming far more massive than observed. AGN feedback provides a mechanism to quench star formation, halting growth, and allowing galaxies to settle into the structures we see today. Webb has observed AGN across a wide range of cosmic epochs, from the nearby universe to the distant early universe. By studying AGN at different stages of cosmic history, astronomers can trace the coevolution of black holes and galaxies. Observations suggest a strong correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge, the dense central concentration of stars. This correlation implies a deep connection between black hole growth and galaxy formation, though the precise nature of this connection is still debated. Does the black hole grow first, suppressing star formation and limiting the galaxy's size? Or does the galaxy form first, funneling gas toward the center and feeding the black hole? Or do both processes occur simultaneously, locked in a feedback loop? Webb's observations are helping to answer these questions by providing detailed measurements of black hole masses, star formation rates, and gas dynamics in galaxies across cosmic time. Galaxies themselves are not isolated islands. They are embedded in a cosmic web, a vast network of filaments and voids that spans the entire observable universe. This structure arose from tiny density fluctuations in the early universe, imprinted during the first moments after the Big Bang. Regions that were slightly denser than average attracted more matter through gravity, becoming denser still. Regions that were slightly less dense than average lost matter to their surroundings, becoming emptier. Over billions of years, this process amplified the initial fluctuations, growing them into the large-scale structure we observe today. Galaxies formed at the intersections of filaments, where gas accumulated and cooled. Voids, the vast empty regions between filaments, contain few galaxies and little matter. The cosmic web is not directly visible. It consists primarily of dark matter and diffuse gas, neither of which emit light. But its presence can be inferred from the distribution of galaxies and from the subtle gravitational lensing of background light. Gravitational lensing occurs when light from a distant object passes through a region of strong gravity, such as a galaxy cluster or a massive filament. The gravity bends the light's path, distorting and magnifying the image of the distant object. By studying these distortions, astronomers can map the distribution of mass, including dark matter, even though the dark matter itself is invisible. Webb has used gravitational lensing to study some of the faintest and most distant galaxies ever observed. The lensing effect, produced by foreground galaxy clusters, magnifies the light from background galaxies, making them bright enough to detect and study in detail. One of the most profound discoveries in cosmology is that the universe had a beginning. This was not always accepted. Throughout much of the 20th century, there was significant debate between proponents of the Big Bang model and proponents of the steady-state model, which held that the universe was eternal and unchanging on large scales, with new matter continuously created to maintain constant density as space expanded. The discovery of the cosmic microwave background radiation in 1965 decisively favored the Big Bang model. The cosmic microwave background, or CMB, is a faint glow of microwave radiation that fills the entire sky. It is the afterglow of the Big Bang, the cooled remnant of the hot, dense plasma that filled the universe during its first few 100,000 years. In the early universe, matter and radiation were tightly coupled. The universe was so hot that atoms could not form. Electrons and protons existed as free particles, forming a plasma that was opaque to light. Photons could not travel far before scattering off electrons, trapped in a dense fog of charged particles. As the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, the temperature dropped below about 3,000 Kelvin, cool enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, rendered the universe transparent. Photons were no longer scattered by free electrons and could travel freely through space. The CMB is the light from this moment, stretched by cosmic expansion from visible wavelengths into the microwave portion of the spectrum. It is the oldest light in the universe, a snapshot of the universe as it appeared when it was less than 1% of its current age. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin in every direction. But it is not perfectly uniform. There are tiny fluctuations, variations in temperature of about 1 part in 100,000. These fluctuations correspond to the density variations in the early universe, the seeds from which all structure grew. Regions that were slightly denser emitted slightly fewer photons, appearing slightly cooler. Regions that were slightly less dense emitted slightly more photons, appearing slightly warmer. By mapping these fluctuations, astronomers can learn about the conditions in the early universe, including its composition, density, and expansion rate. Missions like COBE, WMAP, and Planck have measured the CMB with increasing precision, providing detailed constraints on cosmological models. The fluctuations in the CMB are consistent with the predictions of inflation, a theory that proposes the universe underwent a brief period of exponential expansion during the first fraction of a second after the Big Bang. Inflation was introduced to solve several puzzles in standard Big Bang cosmology, including the horizon problem and the flatness problem. The horizon problem arises because the CMB is nearly uniform across the entire sky, yet regions on opposite sides of the sky were never in causal contact, meaning they could not have exchanged information or equalized their temperatures. Inflation solves this by proposing that all the regions we observe today were once close together, in causal contact, before inflation expanded them to vast separations. The flatness problem arises because the universe appears to be spatially flat, with its density extremely close to the critical density that separates eternal expansion from eventual recollapse. This fine-tuning seems improbable unless something drove the universe toward flatness. Inflation naturally produces a flat universe, because the exponential expansion stretches any initial curvature to negligible levels. Inflation also provides a mechanism for generating the initial density fluctuations. Quantum fluctuations in the inflaton field, the hypothetical field driving inflation, were stretched to macroscopic scales by the exponential expansion. These quantum fluctuations became the classical density variations that later grew into galaxies and clusters. This is one of the most remarkable predictions of inflation. The large-scale structure of the universe originated from quantum mechanical processes occurring on subatomic scales. Observations of the CMB and the distribution of galaxies support this picture, though direct evidence for inflation remains elusive. Detecting primordial gravitational waves, ripples in space-time produced during inflation, would provide strong confirmation, but such waves have not yet been observed. The age of the universe can be calculated from the expansion rate and the density of matter and energy. Current measurements place the age at approximately 13.8 billion years. This figure is derived from observations of the CMB, the distances and redshifts of galaxies, and the abundances of light elements like hydrogen, helium, and lithium, which were synthesized during the first few minutes after the Big Bang in a process called Big Bang nucleosynthesis. The consistency of these independent measurements is one of the great successes of modern cosmology. They all point to the same cosmic history, a universe that began in a hot, dense state and has been expanding and cooling ever since. Webb's observations extend our view of this history to unprecedented depths. By detecting galaxies at redshifts exceeding 13, Webb is observing the universe when it was less than 3% of its current age. This is the era when the first stars and galaxies were forming, transforming the universe from a dark, neutral state to a luminous, ionized one. This transformation, called reionization, occurred gradually over several 100 million years. The first stars emitted ultraviolet radiation energetic enough to ionize surrounding hydrogen, creating bubbles of ionized gas. As more stars formed, these bubbles grew and merged, eventually permeating the entire universe. By about 1 billion years after the Big Bang, reionization was complete and the universe had transitioned to its current ionized state. Understanding reionization requires identifying the sources responsible for ionizing the gas. Early stars and galaxies are the primary candidates, but their contributions remain uncertain. How many ionizing photons did they produce? How much of this radiation escaped their host galaxies to ionize the surrounding intergalactic medium? These questions are difficult to answer because the relevant processes occur on scales ranging from individual stars to entire galaxies, and because the early universe was heterogeneous, with ionization proceeding unevenly across different regions. Webb's spectroscopic observations of early galaxies are providing critical data on the production and escape of ionizing radiation, helping to constrain models of reionization. Reionization marks a phase transition in the universe's evolution, comparable in significance to recombination. Just as recombination rendered the universe transparent, allowing the CMB to escape, reionization transformed the intergalactic medium from neutral to ionized, altering the conditions for subsequent galaxy formation. Ionized gas is hotter and more diffuse than neutral gas, making it harder for small galaxies to retain their gas against the pressure of radiation and stellar winds. This may explain why the number of small galaxies observed in the universe is lower than predicted by simulations of dark matter structure formation. The missing satellites problem, as it is called, may be resolved if ionization and feedback processes suppress the formation or survival of low-mass galaxies. The interplay between dark matter and ordinary matter is critical to understanding galaxy formation. Dark matter provides the gravitational scaffolding that holds structures together, but does not interact with light or ordinary matter except through gravity. Ordinary matter, composed of protons, neutrons, and electrons, can collide, radiate, and cool, allowing it to collapse into dense concentrations like stars and planets. Dark matter cannot do this. It remains distributed in diffuse halos, invisible and intangible, but gravitationally dominant. Simulations of structure formation track the evolution of dark matter halos, showing how they merge and grow over time. These simulations predict a hierarchical process, where small halos form first and then merge to create larger ones. This bottom-up assembly is consistent with observations of galaxy clustering and the cosmic web. But simulations of dark matter alone cannot predict the properties of galaxies. To do that, astronomers must include the physics of ordinary matter, gas dynamics, star formation, supernova feedback, black hole growth, and AGN feedback. These processes are complex and occur on scales much smaller than the dark matter halos, making them difficult to simulate accurately. Current simulations can reproduce many observed properties of galaxies, such as their sizes, masses, and star formation rates, but discrepancies remain. For example, simulations tend to produce galaxies that are too concentrated, with too many stars in their centers. This overconcentration may be alleviated by feedback processes that expel gas from galaxy cores, reducing the efficiency of star formation. But the details of these processes are still being refined. Webb's observations provide essential tests for these simulations. By measuring the properties of galaxies at different cosmic epochs, astronomers can compare observations with predictions and identify where models succeed or fail. Early results from Webb have already revealed discrepancies. Some early galaxies are more massive, more structured, and contain more dust than models predicted. These discrepancies do not necessarily indicate fundamental flaws in our understanding, but they do suggest that certain processes, such as star formation, dust production, or black hole growth, were more efficient in the early universe than current models assume. Refining these models requires iterative comparison with observations, a process that Webb is accelerating. The concept of cosmic scale is not static. As we probe deeper into space and time, we encounter phenomena that challenge our existing frameworks. The discovery of dark energy, for example, was unexpected. Most cosmologists in the 1990s anticipated that the expansion of the universe was slowing down, decelerated by the gravitational pull of matter. The discovery that expansion was accelerating required introducing a new component, dark energy, that had not been predicted by theory. This was not the first time observations forced a revision of cosmological models, and it will not be the last. Science proceeds through a cycle of observation, theory, and refinement. Observations reveal new phenomena. Theories attempt to explain them. Further observations test these theories, revealing successes and failures, prompting further refinement. This cycle is the engine of scientific progress. The true scale of the universe is not merely a matter of distances and sizes. It is also a matter of complexity and diversity. The universe contains structures on every scale, from subatomic particles to galaxy clusters spanning hundreds of millions of light years. It operates according to physical laws that are simultaneously simple and profoundly subtle. Gravity, electromagnetism, and the nuclear forces govern all interactions, yet their combined effects produce phenomena of staggering complexity: stars, planets, life, consciousness. Understanding how complexity emerges from simplicity is one of the deepest questions in science, touching on cosmology, biology, and philosophy. Webb is not merely a telescope. It is an instrument for exploring the boundaries of knowledge. Every image it produces, every spectrum it records, every galaxy it discovers, adds to our understanding of the universe's structure, history, and evolution. But it also reveals the vastness of what we do not know. For every question Webb answers, it raises new ones. How did the first stars form? How did supermassive black holes grow so quickly? What is dark matter? What is dark energy? How common is life in the universe? These questions are not abstract. They are at the heart of humanity's quest to understand its place in the cosmos. The scale of the universe, as revealed by Webb and other instruments, is humbling. The Earth is a tiny speck orbiting an average star in an ordinary galaxy among hundreds of billions of galaxies. The entire observable universe, vast as it is, may be only a small fraction of the total universe, which could extend far beyond the reach of our telescopes, perhaps infinitely. Some cosmological models suggest the universe is not only larger than we can observe, but also more varied, containing regions with different physical constants or even different numbers of dimensions. These ideas, while speculative, are taken seriously by physicists because they emerge naturally from attempts to unify quantum mechanics and general relativity, the two pillars of modern physics. Quantum mechanics governs the behavior of particles on small scales, describing them not as definite objects, but as clouds of probability, existing in superpositions of multiple states until measured. General relativity governs the behavior of space and time on large scales, describing gravity not as a force, but as the curvature of space-time caused by mass and energy. These two theories are extraordinarily successful in their respective domains, but they are fundamentally incompatible. Quantum mechanics is formulated in a fixed space-time background, while general relativity treats space-time as dynamic. Attempts to reconcile them have led to various proposals, including string theory, loop quantum gravity, and others, but none have been conclusively verified. A complete theory of quantum gravity, if achieved, would provide a unified description of all physical phenomena, from the quantum fluctuations in the early universe to the expansion of space itself. Webb's observations of the early universe provide indirect tests of quantum gravity. The density fluctuations imprinted in the CMB and amplified into the cosmic web are thought to originate from quantum fluctuations during inflation. If this is correct, then the large-scale structure of the universe is a macroscopic manifestation of quantum mechanics, a fossil record of processes that occurred at energies and scales far beyond the reach of particle accelerators. By studying the statistical properties of these fluctuations, astronomers can constrain models of inflation and probe the physics of the very early universe, including possible signatures of quantum gravity. The concept of the observable universe is central to understanding cosmic scale. The observable universe is the region from which light has had time to reach us since the Big Bang. Its radius is not simply the age of the universe times the speed of light, because space has been expanding during the time light has been traveling. Accounting for this expansion, the radius of the observable universe is approximately 46 billion light-years, and its diameter is roughly 93 billion light-years. But this is only the part of the universe we can observe. The universe beyond the observable horizon is causally disconnected from us. We can never receive information from those regions because their light has not had time to reach us, and, due to the accelerating expansion driven by dark energy, never will. These distant regions are receding from us faster than the speed of light, not because they are moving through space at superluminal speeds, but because the space between us and them is expanding. General relativity allows space itself to expand at any rate, including rates faster than light. This does not violate special relativity, which restricts the motion of objects through space, not the expansion of space itself. The existence of a cosmic horizon has profound implications. It means the universe we observe is not the entire universe, but only a portion of it. The total universe could be much larger, possibly infinite. It could contain regions vastly different from our own, regions where the density of matter, the strength of dark energy, or even the fundamental constants of physics differ. These ideas are not mere speculation. They arise naturally in models of eternal inflation, where inflation does not end everywhere at once, but continues in some regions while ending in others. Each region where inflation ends becomes a separate bubble universe with its own properties. These bubble universes are causally disconnected from each other, forming a multiverse. The concept of a multiverse is controversial, in part because it is difficult or impossible to test. If other universes are forever beyond our observational reach, can we ever confirm or refute their existence? This is as much a philosophical question as a scientific one. Webb's mission is to observe the universe we can access, the observable universe, and to extract as much information as possible from the light that reaches us. This light carries the imprints of its journey, the elements it passed through, the gravitational fields it traversed, the expansion of space that stretched its wavelength. By decoding these imprints, astronomers reconstruct the history and structure of the cosmos. This is forensic science on the grandest scale, using light as evidence to piece together events that occurred billions of years ago. The process of galaxy formation is not a simple collapse of gas into stars. It is a complex interplay of accretion, feedback, mergers, and environmental effects. Galaxies grow by accreting gas from the intergalactic medium, the diffuse gas that fills the space between galaxies. This gas cools and falls inward, feeding star formation. But star formation itself injects energy back into the gas through supernova explosions and stellar winds, heating it and sometimes expelling it from the galaxy entirely. This feedback regulates star formation, preventing galaxies from converting all their gas into stars too quickly. Galaxies also grow by merging with other galaxies. When two galaxies collide, their stars generally do not collide, because stars are so far apart that the probability of a direct collision is negligible. But the galaxy's gas clouds do collide, compressing and triggering bursts of star formation. The galaxy's dark matter halos merge, and eventually the stellar components merge as well, forming a larger galaxy. Over billions of years, mergers build up massive galaxies from smaller progenitors. The Milky Way itself is the product of such mergers. It has consumed numerous smaller galaxies over its history, and it is currently in the process of absorbing at least two dwarf galaxies, the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy, whose stars are being stripped away and incorporated into the Milky Way's halo. In the distant future, the Milky Way will merge with the Andromeda Galaxy, its nearest large neighbor, located about 2.5 million light-years away. This merger, predicted to occur in about 4.5 billion years, will produce a giant elliptical galaxy, a smooth, featureless blob of stars very different from the Milky Way's current spiral structure. By the time this happens, the Sun will be nearing the end of its life, expanding into a red giant and engulfing the inner planets. Any civilizations in the Milky Way or Andromeda at that time will witness a sky filled with two colliding galaxies, a spectacular display that will unfold over hundreds of millions of years. The diversity of galaxy types reflects the diversity of formation histories and environments. Spiral galaxies like the Milky Way have disks of stars, gas, and dust rotating around central bulges. They are actively forming stars, especially in their spiral arms, which are regions of enhanced density where gas clouds are compressed and triggered to collapse. Elliptical galaxies are smooth and featureless, lacking disks and spiral structure. They contain mostly old stars and little gas, indicating that their star formation ceased long ago. Ellipticals likely formed through mergers of spiral galaxies, which disrupted the disks and mixed the stellar populations into a smooth distribution. Irregular galaxies lack organized structure. They are often small and gas-rich, actively forming stars, and may be the building blocks from which larger galaxies are assembled. Dwarf galaxies, much smaller than the Milky Way, are the most common type of galaxy, but also the faintest and hardest to detect. They play a crucial role in hierarchical assembly, serving as the seeds that merge to form larger galaxies. Webb's observations of galaxy morphology at high redshifts reveal that early galaxies were more irregular and less organized than those in the nearby universe. This is consistent with hierarchical assembly. Early galaxies were smaller and less evolved, still in the process of accumulating mass and settling into stable structures. Over time, as mergers became less frequent and feedback processes quenched star formation in some galaxies, the diversity of galaxy types increased. Today's universe contains galaxies at every stage of evolution, from active star-forming spirals to quiescent ellipticals, reflecting the wide range of histories and environments. The environment in which a galaxy resides has a profound effect on its evolution. Galaxies in dense clusters experience frequent interactions with neighbors, tidal forces that strip away gas, and collisions that trigger starbursts or quench star formation. The intracluster medium, the hot gas that fills galaxy clusters, exerts ram pressure on galaxies moving through it, stripping away their cold gas and halting star formation. This process, called ram pressure stripping, is one reason why cluster galaxies tend to be gas-poor ellipticals and lenticulars, while field galaxies, those in less dense regions, are more often gas-rich spirals. Webb's ability to study galaxies in a variety of environments and at different cosmic epochs allows astronomers to disentangle the effects of mass, environment, and cosmic time on galaxy evolution. Galaxy clusters themselves are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies, along with vast amounts of hot gas and dark matter, with total masses reaching a quadrillion solar masses or more. Clusters form at the intersections of the cosmic web's filaments, where matter accumulates and collapses under its own gravity. The hot intracluster gas, heated by gravitational compression and by shocks from mergers, emits X-rays detectable by space telescopes like Chandra and XMM Newton. The dark matter distribution can be mapped through gravitational lensing, as the cluster's gravity bends the light from background galaxies. By combining X-ray, optical, and lensing observations, astronomers can measure the distribution of both ordinary and dark matter in clusters, testing models of structure formation and constraining the properties of dark matter itself. Some clusters exhibit dramatic evidence of recent mergers. The bullet cluster, for example, consists of two clusters that collided and passed through each other. The hot gas from each cluster collided and was slowed by friction, remaining near the collision site. But the dark matter, which does not interact except through gravity, passed through unimpeded, continuing outward with the galaxies. Gravitational lensing maps show that the majority of the mass, the dark matter, is displaced from the hot gas, providing direct evidence that dark matter and ordinary matter are distinct and that dark matter interacts only weakly with itself. This observation is one of the strongest pieces of evidence for dark matter and has been difficult to explain with alternative theories like modified gravity. Webb's infrared sensitivity makes it particularly effective at studying dusty environments, such as the centers of galaxies where star formation is often obscured. Dust absorbs ultraviolet and visible light from young stars and re-emits it in the infrared. By observing in the infrared, Webb can detect this reprocessed light, revealing star formation that would be invisible at shorter wavelengths. This capability is crucial for constructing a complete census of star formation throughout cosmic history. Many of the most active star-forming galaxies, known as starburst galaxies or luminous infrared galaxies, are heavily obscured by dust. Hubble could detect them only faintly or not at all, but Webb sees them clearly, allowing detailed studies of their star formation rates, gas content, and internal structure. The distribution of elements in the universe provides another window into cosmic history. Hydrogen and helium, the lightest elements, were synthesized during the first few minutes after the Big Bang, when the universe was hot enough for nuclear reactions, but not so hot that nuclei were immediately torn apart by radiation. As the universe expanded and cooled, a brief window opened during which protons and neutrons could combine into heavier nuclei. The most abundant product was helium-4, with trace amounts of deuterium, helium-3, and lithium-7. The relative abundances of these light elements depend sensitively on the density of ordinary matter during nucleosynthesis. By measuring these abundances, astronomers can infer the density of baryons, the protons and neutrons that make up ordinary matter. This density, combined with the total density inferred from the CMB and structure formation, confirms that ordinary matter constitutes only a small fraction of the universe's energy content, with dark matter and dark energy dominating. Heavier elements, from carbon to uranium, were not produced in the Big Bang. They were synthesized inside stars or during supernova explosions. Carbon and oxygen are produced in the cores of massive stars through fusion reactions. When these stars explode as supernovae, they not only disperse the carbon and oxygen, but also synthesize even heavier elements through rapid neutron capture, a process called the R process. Elements like gold, platinum, and uranium are thought to form primarily in neutron star mergers, extraordinarily violent events that occur when two neutron stars orbit each other and eventually collide. These mergers produce conditions of extreme temperature and density, allowing rapid neutron capture to build up heavy nuclei. Webb has observed the aftermath of neutron star mergers, detecting the infrared emission from freshly synthesized heavy elements. These observations confirm that neutron star mergers are indeed major sources of heavy elements and provide insight into the conditions during these events. The concept of nucleosynthesis, the creation of elements, ties directly to the concept of scale. The universe began with the simplest building blocks, and over billions of years, it has constructed ever more complex structures. From quarks and electrons emerged protons, neutrons, and atoms. From atoms emerged molecules. From molecules emerged dust grains, asteroids, planets. From planets, at least on Earth and possibly elsewhere, emerged life. From life emerged intelligence and civilization. This hierarchical construction is a fundamental feature of cosmic evolution. Each level builds on the previous one, enabled by the physical laws that govern interactions at each scale. Webb's observations span this hierarchy. It studies the formation of stars, where atoms are fused into new elements. It studies the formation of planetary systems, where dust grains collide and accrete to form planets. It even studies the atmospheres of exoplanets, planets orbiting stars other than the Sun, searching for molecules that might indicate habitability or even biological activity. Thousands of exoplanets have been discovered over the past few decades, orbiting stars across the galaxy. They range from gas giants larger than Jupiter to rocky worlds smaller than Earth. Some orbit in their star's habitable zone, the region where temperatures allow liquid water to exist on a planet's surface. Liquid water is considered essential for life as we know it, though life might exist in other forms or under other conditions. Detecting life on an exoplanet is extraordinarily challenging. The planet is too faint to image directly, overwhelmed by the glare of its host star. Instead, astronomers study the planet indirectly, through its effects on the star's light. When a planet transits in front of its star, blocking a tiny fraction of the star's light, that dimming can be measured. By observing multiple transits, astronomers can determine the planet's size and orbital period. During a transit, some of the star's light passes through the planet's atmosphere. Molecules in the atmosphere absorb specific wavelengths, imprinting their signatures onto the star's spectrum. By comparing the spectrum during a transit with the spectrum outside of transit, astronomers can identify which molecules are present in the planet's atmosphere. Webb's sensitivity to infrared light allows it to detect molecules like water, methane, carbon dioxide, and ammonia, which absorbs strongly in the infrared. If a planet's atmosphere contains molecules associated with biological activity, such as oxygen, ozone, methane in the presence of oxygen, or more exotic biosignatures. This could indicate the presence of life. However, distinguishing biological from non-biological sources is difficult. Oxygen, for example, can be produced by photosynthesis, a biological process, but can also be produced by the photodissociation of water vapor in a planet's atmosphere, a non-biological process. Multiple lines of evidence would be needed to make a convincing case for life. Webb is conducting a survey of potentially habitable exoplanets, measuring their atmospheric compositions and searching for biosignatures. Even if no definitive signs of life are found, these observations will constrain the prevalence of life in the galaxy and guide future missions designed to search for life. The scale of the exoplanet search is staggering. Thousands of planets have been discovered, but these are only the ones we can detect with current technology. Most planets are too small, too far from their stars, or orbit stars too faint for current instruments to detect. The true number of planets in the Milky Way is estimated to be in the hundreds of billions, with tens of billions potentially in habitable zones. If even a tiny fraction of these harbor life, the galaxy could be teeming with living worlds. The discovery of even one unambiguous example of extraterrestrial life, whether microbial or complex, would transform our understanding of biology, philosophy, and our place in the universe. It would confirm that life is not unique to Earth, but a common outcome of cosmic evolution. Webb's exploration of exoplanet atmospheres is one part of a broader effort to understand planetary systems. Another part involves studying protoplanetary disks, the rotating disks of gas and dust that surround young stars and from which planets form. These disks are the birthplaces of planetary systems, and understanding their properties is key to understanding how planets form and evolve. Webb's infrared vision allows it to penetrate the dust in these disks, revealing their internal structure and the early stages of planet formation. Observations have detected gaps and rings in protoplanetary disks, features that may indicate the presence of forming planets. As a planet orbits within a disk, its gravity clears a gap, sweeping up or scattering material in its path. The detection of such gaps provides indirect evidence for planets that are too small and faint to image directly. The process of planet formation is not fully understood. It begins with the accumulation of dust grains into larger particles through collisions and electrostatic forces. These particles grow into pebbles, then boulders, then kilometer-sized planetesimals. Planetesimals collide and merge, forming planetary embryos, which eventually grow into planets. But many details remain unclear. How do dust grains stick together despite destructive collisions? How do planetesimals grow large enough to gravitationally attract more material? How do gas giant planets, which require massive cores to accumulate thick atmospheres, form before the gas in the disk is dispersed? These questions are being addressed through a combination of observations, laboratory experiments, and computer simulations. Webb's observations of protoplanetary disks at various stages of evolution provide snapshots of the planet formation process, allowing astronomers to test and refine their models. The Milky Way contains billions of planetary systems, each potentially unique. Some systems have planets in compact orbits, huddled close to their stars. Others have planets spread over vast distances. Some have gas giants in the inner regions, contrary to the layout of our solar system, where gas giants are farther out. These hot Jupiters, as they are called, may have formed farther from their stars and migrated inward, driven by interactions with the protoplanetary disk or with other planets. The diversity of planetary systems suggests that planet formation is influenced by many factors, including the mass and composition of the protoplanetary disk, the presence of nearby stars, and the timing and nature of dynamical interactions between forming planets. Our solar system's structure, with rocky planets close to the sun and gas giants farther out, may not be typical. It may be the result of specific conditions in the solar nebula, the disk from which the solar system formed, or of dynamical events early in the solar system's history. Some models propose that the outer planets, Jupiter and Saturn, underwent significant migrations, moving inward and then outward again, sculpting the architecture of the solar system and scattering smaller bodies into the asteroid belt and the Kuiper belt. These migrations may have played a role in the delivery of water to the inner solar system, including Earth, through the scattering of icy bodies inward. Water, essential for life, is common in the outer solar system but rare in the inner regions, where high temperatures vaporize it. If Earth's water was delivered by comets or asteroids from the outer solar system, then the migrations of the giant planets indirectly enabled the emergence of life on Earth. The scale of the solar system is itself humbling. The Sun contains 99.86% of the solar system's mass. The planets, moons, asteroids, and comets are mere crumbs by comparison. Yet these crumbs harbor immense complexity. Jupiter's moon Europa has a subsurface ocean beneath its icy crust, kept liquid by tidal heating from Jupiter's gravity. Saturn's moon Enceladus also has a subsurface ocean and ejects plumes of water vapor and ice particles from cracks in its south polar region. Both moons are considered potential habitats for life. Mars, now a cold, dry desert, has abundant evidence of ancient rivers, lakes, and possibly oceans, suggesting it was once warmer and wetter, conditions that might have supported life billions of years ago. The search for life in the solar system is therefore not limited to exoplanets, but includes these nearby worlds, which can be studied in much greater detail. Webb's observations of objects in the outer solar system, such as Kuiper belt objects and comets, provide information about the primitive materials from which the solar system formed. These objects are icy remnants from the era of planet formation, preserved in the cold outer reaches where they have remained largely unchanged for billions of years. By studying their compositions and structures, astronomers can learn about the conditions in the solar nebula and the processes that built the planets. Comets, which originate in the Kuiper belt or the even more distant Oort cloud, occasionally fall inward toward the Sun, where sunlight vaporizes their ices and creates glowing tails. Observations of comets can reveal the composition of these primitive ices, including the ratios of isotopes, which provide clues about the temperature and environment in which the ice is formed. The Kuiper belt, a region beyond Neptune filled with icy bodies, is analogous to the asteroid belt but far larger and more massive. It is home to Pluto, once considered the ninth planet but now classified as a dwarf planet, along with thousands of other objects ranging in size from tiny icebergs to worlds several hundred kilometers across. The Kuiper belt is not the end of the solar system. Beyond it lies the Oort cloud, a vast spherical shell of icy bodies extending halfway to the nearest star. The Oort cloud is thought to contain trillions of comets, the remnants of the protoplanetary disk scattered outward by gravitational interactions with the giant planets. The Oort cloud has never been directly observed, because its objects are too distant and too faint, but its existence is inferred from the orbits of long-period comets, which fall inward from all directions with orbital periods of thousands or millions of years. The scale of the Oort cloud underscores the vastness of even our local cosmic neighborhood. The solar system's influence, defined by the reach of the Sun's gravity, extends roughly 1 light-year, about a quarter of the distance to Proxima Centauri. This region, encompassing the Oort cloud, is largely empty, a dark expanse traversed only occasionally by the faint light of distant stars. Beyond this lies interstellar space, the region between stars, filled with diffuse gas, dust, and magnetic fields. Interstellar space is not empty, but it is extraordinarily tenuous, with densities far lower than the best laboratory vacuums on Earth. Interstellar gas and dust play crucial roles in the life cycle of matter in the galaxy. Gas clouds collapse to form stars. Stars synthesize heavy elements and return them to space through stellar winds and supernovae. Dust grains form in the cool outflows of evolved stars and in supernova ejetions, incorporating heavy elements into solid particles. These grains serve as catalysts for chemical reactions, enabling the formation of complex molecules, including those necessary for life. In dense molecular clouds, where dust shields the interior from ultraviolet radiation, molecules like water, ammonia, methanol, and even amino acids and sugars have been detected. These molecules, some of which are precursors to life, are synthesized in space through chemical processes on the surfaces of dust grains and in the gas phase. They are then incorporated into comets, asteroids, and eventually planets, seeding them with organic material. The chemical complexity of interstellar space was unexpected. For much of the 20th century, space was assumed to be chemically simple, composed mostly of atoms and simple molecules. But radio telescopes, which detect the rotational transitions of molecules, revealed a rich molecular inventory. To date, more than 200 different molecules have been detected in space, ranging from simple diatomic molecules like carbon monoxide to complex organic molecules with dozens of atoms. The presence of these molecules raises the possibility that the building blocks of life are widespread in the galaxy, delivered to planets through impacts by comets and asteroids. This hypothesis, called panspermia in its strong form, suggests that life itself might spread between planets or even between star systems, carried by such impacts. While this remains speculative, the evidence for organic chemistry in space is strong and growing. Webb's ability to detect complex molecules in space, including in the atmospheres of exoplanets and in interstellar clouds, contributes to our understanding of the chemical pathways that lead to life. By identifying which molecules are present in different environments and at different stages of stellar and planetary evolution, astronomers can trace the chemical evolution of the galaxy and assess how common the ingredients for life might be. The question of life's prevalence in the universe is intimately connected to the question of the universe's scale. If life is common, arising wherever conditions are suitable, then the sheer number of planets in the galaxy suggests that life should be widespread, perhaps numbering in the millions or billions of instances. If life is rare, requiring highly specific conditions or improbable events, then it might be limited to a handful of worlds or even unique to Earth. The lack of any confirmed detection of extraterrestrial life, despite decades of searching, is sometimes called the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" If the galaxy is so large and so old, and if life is common, why have we not detected any signs of it, such as radio signals from advanced civilizations? Many solutions to the Fermi paradox have been proposed. Perhaps life is common, but intelligent, technological civilizations are rare, because intelligence requires a specific evolutionary pathway that is difficult to achieve. Perhaps civilizations arise frequently, but self-destruct before they can expand into space or send detectable signals. Perhaps they exist, but are too far away for us to detect, or they use communication methods we have not anticipated. Perhaps they are deliberately avoiding contact, or we're living in a simulation, or we are the first. Each of these possibilities has implications for how we think about the universe and our place in it. Webb is not designed to search for signals from extraterrestrial civilizations, but its observations of exoplanet atmospheres and the prevalence of habitable environments provide data relevant to estimating the likelihood of life elsewhere. If many planets are found to have conditions suitable for life, this increases the probability that life exists, even if we have not yet detected it. If few planets meet the necessary criteria, this suggests life might be rare. These findings will guide future missions, including ground-based telescopes, space missions, and possibly interstellar probes that aim to search for life more directly. The scale of the search for life is matched by the scale of the search for understanding the universe's ultimate fate. Current observations suggest the universe will expand forever, driven by dark energy. As it expands, galaxies will recede from each other, eventually disappearing beyond each other's cosmic horizons. The CMB will fade and cool, eventually becoming undetectable. Stars will exhaust their fuel and die. The longest-lived stars, red dwarfs, will burn for trillions of years, but even they will eventually fade. After all stars have died, the universe will enter an era dominated by black holes, which will slowly evaporate through Hawking radiation, a quantum process by which black holes emit particles and lose mass. The timescale for this evaporation is staggering, exceeding 10 to the power of 100 years for the most massive black holes. After black holes have evaporated, the universe will consist only of photons, neutrinos, and a few stable particles like electrons and positrons, existing in a state of maximum entropy, a cold, dark, and featureless expanse. This ultimate fate, called the heat death of a universe, is the logical conclusion of the second law of thermodynamics, which states that entropy, disorder, always increases in a closed system. But this picture assumes the properties of dark energy remain constant. If dark energy changes over time, the universe's fate could be different. If dark energy weakens, the expansion might slow or even reverse, leading to a big crunch. If dark energy strengthens, the expansion could accelerate without bound, eventually tearing apart galaxies, stars, planets, and even atoms in a scenario called the Big Rip. Observations of distant supernovae and the expansion history of the universe are being used to test these possibilities, measuring how the expansion rate has changed over time. So far, the data are consistent with a cosmological constant, a form of dark energy that does not change, but uncertainties remain. Future observations, including those from Webb and upcoming missions, will refine these measurements, narrowing the range of possibilities for the universe's ultimate fate. The philosophical implications of the universe's scale and fate are profound. Humanity exists on a small planet orbiting an average star in an ordinary galaxy, a galaxy that is one among hundreds of billions. The sun will shine for another 5 billion years, but the universe will continue for trillions or even infinite years beyond that. Human civilization, recorded history spanning only a few thousand years, is an infinitesimal flicker in cosmic time. Yet despite this insignificance, humans have developed the ability to observe, measure, and understand the universe. We have discovered the laws of physics, traced the history of the cosmos, and peered back to within a few 100 million years of the beginning. This capacity for understanding is itself remarkable, perhaps unique among life in the galaxy or even the universe. Webb represents the culmination of decades of effort, ingenuity, and collaboration. Its design, construction, and operation involved thousands of scientists, engineers, and technicians from around the world. Its mirrors were polished to nanometer precision. Its instruments were tested at cryogenic temperatures. Its deployment, a complex sequence involving the unfolding of its sun shield and the alignment of its mirror segments, was executed flawlessly despite numerous opportunities for failure. The success of Webb is a testament to human ingenuity and the drive to explore and understand. But Webb is not the end. It is a step, a single instrument in an ongoing quest that spans generations. Future telescopes, both ground-based and space-based, are being planned and built. These instruments will have even greater sensitivity, larger mirrors, and more advanced detectors. They will observe in wavelengths inaccessible to Webb, from radio to X-rays, each wavelength revealing different aspects of the universe. Together, these instruments will construct an ever more detailed picture of cosmic structure, history, and evolution. The scale of the universe is not merely a fact to be recorded. It is a context within which all other knowledge must be understood. Every process, every structure, every phenomenon exists within this vast framework. The formation of stars, the evolution of galaxies, the emergence of life, all occur against the backdrop of cosmic expansion, dark matter, dark energy, and the laws of physics. Understanding the universe's scale allows us to see how these processes fit together, how they influence one another, and how they have shaped the cosmos into what it is today. Webb's observations of distant galaxies are not isolated snapshots. They are pieces of a larger puzzle, a puzzle that astronomers are painstakingly assembling. Each galaxy provides information about its environment, its history, its interactions. By observing thousands of galaxies across different epochs, astronomers can reconstruct the statistical properties of galaxy populations, identifying trends and correlations that reveal underlying physical processes. For example, The relationship between a galaxy's mass and its star formation rate changes with cosmic time, indicating that the processes regulating star formation have evolved. Early galaxies formed stars more rapidly relative to their masses than galaxies today, suggesting that feedback processes have become more effective over time. These statistical studies require large samples, which is why Webb conducts surveys observing many galaxies in a single field of view. By pointing at a single region of sky for extended periods, Webb can detect even the faintest objects, building up catalogs of thousands of galaxies with measured redshifts, brightnesses, colors, and spectra. These catalogs are then analyzed to extract patterns and test theories. The interplay between observation and theory is iterative. Theories make predictions, observations test them, and discrepancies prompt refinements. This process has driven cosmology from speculative field to a precision science over the past century. The precision of modern cosmology is remarkable. We know the age of the universe to better than 1%. We know its composition, the fractions of dark energy, dark matter, and ordinary matter to a few percent. We know the rate of its expansion, the Hubble constant, to within a few percent, though there's an ongoing tension between measurements using different methods. We know the amplitude and spectrum of density fluctuations imprinted in the CMB and grown into the cosmic web. We can predict the abundances of light elements produced in Big Bang nucleosynthesis and compare them with observations, finding excellent agreement. These successes demonstrate that our basic picture of cosmic history, from the Big Bang through inflation, recombination, reionization, and structure formation, is fundamentally correct. Yet significant mysteries remain. The nature of dark matter and dark energy is unknown. The mechanisms by which the first stars and black holes formed are uncertain. The rate of expansion measured locally using supernovae disagrees slightly with the rate inferred from the CMB, a discrepancy called the Hubble tension. This tension could indicate new physics, such as a change in dark energy over time, or the existence of additional relativistic particles in the early universe. Or it could be due to systematic errors in one or both measurements. Resolving this tension is a major focus of current research. Another mystery involves the formation of structure on the smallest scales. Simulations of dark matter predict the existence of numerous low-mass halos, far more than the number of small galaxies observed. This missing satellites problem could indicate that our understanding of dark matter is incomplete, or it could be resolved by including the effects of baryonic physics, such as supernova feedback, which could suppress the formation of stars and low-mass halos, rendering them invisible. Webb's observations of faint, distant galaxies are helping to address this problem by detecting some of the smallest and faintest galaxies in the early universe, testing whether their abundance matches predictions. The interplay between dark matter and baryonic matter is subtle. Dark matter provides the gravitational potential wells into which baryonic matter falls. But baryonic matter can respond to pressure, magnetic fields, and radiation, allowing it to redistribute and even escape from shallow potential wells. This redistribution affects the structure of galaxies and the distribution of matter on small scales. Modeling these processes requires sophisticated simulations that track both dark matter and gas, including the complex physics of star formation, feedback, and chemical enrichment. Such simulations are computationally expensive, often requiring millions of processor hours on supercomputers, and they're continually being refined as computational power and physical understanding improve. The cosmic web itself, the large-scale structure of filaments and voids, is a manifestation of the initial density fluctuations amplified by gravity. These fluctuations are thought to have originated from quantum fluctuations during inflation, stretched to macroscopic scales by exponential expansion. The statistical properties of these fluctuations, such as their amplitude and scale dependence, are imprinted in the CMB and in the distribution of galaxies. By measuring these properties, astronomers can test models of inflation and constrain the physics of the very early universe. Different inflationary models predict different patterns of fluctuations, and precise observations can distinguish between them. One key observable is the spectral index of the fluctuations, which describes how the amplitude varies with scale. A scale invariant spectrum, where the amplitude is the same on all scales, is predicted by the simplest inflationary models. Observations indicate a slight deviation from scale invariance, with slightly less power on large scales than on small scales, consistent with predictions of slow-roll inflation, where the inflatant field rolls slowly down a potential energy curve. Another key observable is the amplitude of primordial gravitational waves, which would have been generated during inflation and would leave a distinctive imprint on the polarization of the CMB. Detecting this signal, called the B-mode polarization, is a major goal of current and future CMB experiments. So far, no primordial B-mode signal has been detected, but upper limits have been placed on its amplitude, constraining the energy scale of inflation. Webb's observations, while focused on galaxies and stars, contribute to cosmology by providing measurements of the expansion history and the growth of structure. By measuring the distances and redshifts of galaxies and supernovae, Webb helps refine the cosmic distance ladder, the sequence of methods used to measure distances at increasing scales. This ladder begins with parallax measurements of nearby stars, extends through Cepheid variables in nearby galaxies, and reaches distant galaxies through supernovae and other standard candles. Each step relies on the previous one, and uncertainties accumulate. Improving the precision of distance measurements at each step reduces the overall uncertainty and helps resolve tensions like the Hubble tension. The scale revealed by Webb is not static. It is dynamic, evolving, and interconnected. Galaxies are not isolated objects, but nodes in a vast network, linked by filaments of dark matter and gas. They grow through accretion and mergers, they interact with their environments, and they influence each other through gravitational forces and feedback. Stars are born from gas clouds, live for millions or billions of years, and die in explosions or slow fades, returning their material to space. Elements are synthesized, dispersed, and recycled, gradually enriching the universe with heavy elements. Planets form around stars, some of which develop conditions suitable for life. Life, if it exists widely, adds another layer of complexity and connectivity, potentially spreading across planets, star systems, and eventually galaxies. This interconnectedness extends to the fundamental laws of physics. Gravity shapes the large-scale structure of the universe, but quantum mechanics governs the behavior of individual particles. Electromagnetism binds atoms into molecules and powers the radiation from stars. The strong and weak nuclear forces govern the reactions inside stars and the decay of radioactive elements. These forces operate on vastly different scales, from the subatomic to the cosmic, yet they are all interconnected aspects of a unified physical reality. Understanding this unity is the ultimate goal of theoretical physics, a goal pursued through efforts to develop a theory of everything, a single framework that encompasses all forces and particles. String theory is one candidate for such a framework. It proposes that the fundamental constituents of reality are not point particles, but tiny, vibrating strings, whose different modes of vibration correspond to different particles. String theory requires additional spatial dimensions beyond the familiar three, dimensions that are compactified, curled up on scales so small that they have not been detected. The theory is mathematically elegant, but notoriously difficult to test, because its predictions involve energies far beyond the reach of current particle accelerators. Despite this, it has provided insights into quantum gravity, black hole thermodynamics, and the holographic principle, which suggests that the information in a volume of space can be encoded on its boundary. Loop quantum gravity is another approach, which attempts to quantize spacetime itself, representing it as a network of discrete loops at the Planck scale, the smallest scale at which our current understanding of physics applies. This discreteness could resolve singularities, such as the one at the center of a black hole or at the Big Bang, replacing them with quantum transitions. Loop quantum gravity makes testable predictions, such as modifications to the propagation of light at extremely high energies, which could be detected by observations of gamma-ray bursts or other energetic phenomena. So far, no such modifications have been observed, but the search continues. The question of whether a theory of everything exists or whether physics will remain a patchwork of different theories applicable in different regimes is open. It is possible that the quest for unification will succeed, revealing a single elegant framework from which all of physics emerges. It is also possible that different domains of physics are fundamentally separate, connected only through approximate correspondences and effective theories. Either outcome would be profound, reshaping our understanding of reality. Webb's contribution to this quest is indirect but significant. By observing the early universe, Webb provides data on the conditions and processes that prevailed at energies and densities far beyond those accessible in laboratories. These observations constrain models of the early universe, including models of inflation, phase transitions, and the production of matter and antimatter. They probe the frontier where quantum mechanics, general relativity, and particle physics converge, offering glimpses into regimes where new physics might emerge. The scale of the universe, as Webb reveals it, is both a challenge and an invitation. It challenges our intuitions, our cognitive limits, and our technological capabilities. Distances measured in billions of light years, timescales spanning billions of years, energies and densities far beyond terrestrial experience. These are not concepts that human minds evolved to grasp. Yet we have developed the tools, mathematical, observational, and conceptual, to explore and understand them. This capacity is a defining feature of human civilization, a capacity that has grown steadily over millennia, from early observations of the motions of stars and planets to the precise measurements of distant galaxies and the cosmic microwave background. Webb is a tool in this ongoing exploration, a machine designed to extend human perception across gulfs of space and time. Its observations are not mere images or data points. They are evidence, pieces of a larger argument about the structure and history of the cosmos. Each observation refines our models, tests our theories, and reveals new questions. The process is cumulative, each generation building on the work of the previous one, pushing the boundaries of knowledge outward. The true scale of the universe, the full extent of its size, complexity, and diversity, may never be fully known. The observable universe, vast as it is, represents only a finite portion of the total universe, which may be infinite. The processes we observe, star formation, galaxy evolution, the expansion of space, may be only a subset of phenomena that occur elsewhere, in regions beyond our horizon or in dimensions inaccessible to us. The laws of physics we have discovered may be local, applicable only in our region of the universe or in our particular epoch. These possibilities, while speculative, remind us that our knowledge is provisional, subject to revision as new observations and new theories emerge. But this uncertainty does not diminish the value of what we have learned. The universe, as we understand it today, is a place of staggering scale and complexity, governed by physical laws that we can discover and test. It is a universe that emerged from a hot, dense state billions of years ago and has been expanding and evolving ever since. It is a universe filled with galaxies, stars, planets, and possibly life. It is a universe where matter and energy interact according to precise mathematical rules, rules that we can write down and use to make predictions. This understanding, incomplete though it may be, is a monumental achievement, the product of centuries of observation, experimentation, and thought. Webb's mission continues. Every day, it observes new targets, collects new data, and contributes to this ongoing project of understanding. Its discoveries will be analyzed, debated, and integrated into the ever-evolving picture of the cosmos. Future instruments will build on its legacy, observing deeper, with greater precision, and across broader wavelength ranges. The quest to understand the true scale of the universe will continue, driven by curiosity, by the desire to know, and by the recognition that understanding the cosmos is inseparable from understanding ourselves. The scale of the universe is not a single dimension, but a multidimensional tapestry of space, time, energy, and information. It encompasses not only physical extent, but also temporal depth, causal structure, and organizational complexity. From the Planck scale, the smallest meaningful length in physics, to the cosmic horizon, the farthest extent we can observe spans roughly 60 orders of magnitude. From the Planck time, the smallest meaningful duration, to the age of the universe, spans roughly 60 orders of magnitude in time. Within this vast range, structures exist at every intermediate scale, each with its own characteristic processes and dynamics. Subatomic particles, atoms, molecules, cells, organisms, planets, stars, galaxies, clusters, superclusters, and the cosmic web, each level of this hierarchy exhibits emergent properties, features that arise from the collective behavior of components at smaller scales, but cannot be predicted from those components alone. Temperature, for example, is an emergent property of the random motions of atoms. Life is an emergent property of chemical reactions in cells. Galaxies are emergent structures arising from the gravitational collapse of dark matter halos and the complex physics of gas, cooling, and star formation. Understanding emergence, how complexity arises from simplicity, is one of the central challenges in science, spanning physics, biology, and even social sciences. Webb's observations contribute to this understanding by revealing the processes that govern structure formation across cosmic history. How do simple distributions of gas and dark matter evolve into the rich variety of galaxies we observe? How do stars form from molecular clouds? How do planetary systems assemble from protoplanetary disks? How do chemical elements synthesize and spread through galaxies? Each of these questions involves understanding how interactions at one scale give rise to structures at a larger scale, a process that requires integrating knowledge from multiple domains of physics, from quantum mechanics to hydrodynamics to general relativity. The scale of time is as profound as the scale of space. The universe is 13.8 billion years old, but stars will continue to form for trillions of years, and black holes will persist for unimaginably longer, until they evaporate through Hawking radiation on timescales exceeding 10 to the power of 100 years. Humanity's existence occupies an infinitesimal slice of this vast temporal expanse. Recorded history spans only about 5,000 years. The entire span of human evolution, from the emergence of Homo sapiens to the present, is only a few 100,000 years. The Sun, by contrast, is 4.6 billion years old, and the universe is 3 times older still. Placing human history within this cosmic timeline underscores our ephemerality, but also our uniqueness. We exist at a time when the universe is filled with stars and galaxies, a time when life can emerge and evolve, a time when the universe is neither too hot nor too cold, too young nor too old. This epoch, sometimes called the Stelliferous Era, is the age when the universe is most hospitable to complexity and perhaps to life. In the far future, long after the last stars have died, the universe will be a vastly different place. No new stars will form, because all the available gas will have been locked up in dead stellar remnants or dispersed by galactic winds. Galaxies will fade from view, their stars exhausted. The cosmic background radiation will cool to near absolute zero, imperceptible against the blackness of space. Any civilizations existing in that distant era, if they survive, will face challenges inconceivable to us today. Harvesting energy from dwindling sources, perhaps from the slow decay of protons or the evaporation of black holes. Their concept of the universe, shaped by an environment so different from ours, will be fundamentally alien. Yet even in such a far future, the laws of physics will remain. Entropy will continue to increase, but information will persist, at least until it is scrambled by quantum processes or lost beyond event horizons. The universe's history, encoded in its structure and evolution, will leave traces, fossils of a time when stars shone and galaxies collided. Whether any intelligence will exist to decipher those traces is unknown, but the possibility underscores the deep connection between information, entropy, and the nature of reality. Webb's observations are themselves a form of information extraction. Photons, emitted by distant galaxies billions of years ago, traverse the universe and enter Webb's mirrors. There they are focused, detected, and transformed into data, streams of numbers encoding brightness, wavelength, and position. This data is transmitted to Earth, where it is analyzed, interpreted, and transformed into images and spectra. These images and spectra are then studied by astronomers, who extract physical properties like mass, temperature, composition, and distance. This chain, from photon to image to knowledge, is the process by which we learn about the universe. It is a process mediated by technology, by telescopes and detectors and computers, but it is also a process mediated by human cognition, by our ability to recognize patterns, formulate hypotheses, and test them against evidence. The scale of the universe, as revealed by Webb, is ultimately a scale revealed by human effort and ingenuity. The universe does not announce its properties. It must be interrogated painstakingly and systematically through observation and experiment. Every measurement, every image, every spectrum is the result of choices. Where to point the telescope, how long to observe, which instruments to use, how to process the data. These choices are guided by scientific questions, by theories that make predictions, by the desire to understand specific phenomena. Webb's scientific program, the selection of its targets and observations, was developed over years by committees of astronomers, debating priorities, weighing scientific merit, and balancing competing interests. The result is a mission that addresses a broad range of questions, from the formation of the first galaxies to the atmospheres of exoplanets. But every observation is purposeful, designed to advance specific scientific goals. This purposefulness distinguishes science from other modes of inquiry. Science is not passive contemplation, but active investigation. It involves formulating questions, designing experiments or observations to answer them, and interpreting results in light of existing knowledge. It is a collective enterprise involving collaboration across institutions, nations, and disciplines. No single person or group could build and operate a mission like Webb. It requires expertise in optics, cryogenics, electronics, software, data analysis, and astrophysics, among other fields. It requires funding, political support, and public engagement. It is a testament to what humanity can achieve when resources and intellect are directed toward a common goal. The images produced by Webb are often described as beautiful, and they are. The towering pillars of the Carina Nebula, the delicate spiral arms of distant galaxies, the intricate rings of protoplanetary disks. These images evoke aesthetic responses, feelings of awe and wonder. But they are also scientific documents, rich with information waiting to be decoded. Every pixel in a Webb image corresponds to a measurement, a count of photons detected at a specific wavelength and location. By analyzing these measurements, astronomers extract quantitative information, temperatures, densities, velocities, chemical compositions. This dual nature, aesthetic and scientific, is part of what makes astronomy compelling. It engages both the intellect and the emotions, satisfying both the desire to understand and the desire to experience beauty. The scale of the universe is not only a scientific fact, but also a cultural and philosophical one. It shapes how we think about ourselves, our place, and our significance. The realization that Earth is not the center of the universe, that the Sun is not unique, that the Milky Way is one among billions of galaxies, each containing billions of stars, has profound implications. It suggests that we are not special, at least not in any cosmic sense. We are products of ordinary physical processes occurring on an ordinary planet, in an ordinary galaxy, in an ordinary region of space. This perspective, sometimes called the Copernican principle or the principle of mediocrity, has been reinforced by every major discovery in astronomy. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. There is no center. Every point in space has an equal claim to being the origin of the Big Bang. Yet this perspective coexists with another, that life, and especially intelligent life, might be rare or even unique. Despite the vast number of stars and planets, we have no confirmed evidence of life beyond Earth. This could mean life is common but hard to detect, or it could mean life is exceedingly rare, arising only under specific conditions that are seldom met. If life is rare, then Earth and humanity might be precious, not cosmically, but as isolated instances of a phenomenon that occurs only occasionally across the vastness of space and time. This tension between cosmic insignificance and potential uniqueness is unresolved and may remain so until we detect life elsewhere, or until we explore enough of the galaxy to conclude that we are alone. The scale of the universe also raises questions about the future of humanity and civilization. If the universe is so vast, and if travel at relativistic speeds is possible, could humanity or its descendants eventually spread across the galaxy, colonizing planets, building megastructures, and harnessing the energy of stars? Such visions are staples of science fiction, but they're grounded in real possibilities, at least in principle. There are no known physical laws that prohibit interstellar travel or the construction of Dyson spheres or other megastructures. The challenges are practical. Developing propulsion systems capable of reaching significant fractions of the speed of light, sustaining life during journeys lasting centuries or millennia, and overcoming the vast distances and harsh environments of space. Whether such expansion will occur depends on choices humanity makes in the coming centuries, choices about resource allocation, technological development, and societal values. It also depends on whether humanity survives the challenges it currently faces, including climate change, resource depletion, and geopolitical conflict. The universe, vast and ancient, is indifferent to these challenges. It will continue expanding, stars will continue forming and dying, galaxies will continue evolving, regardless of what happens on Earth. But for humanity, these challenges are existential, determining whether we remain confined to a single planet or eventually venture outward. Webb's observations, while focused on the distant universe, also provide context for understanding our local cosmic environment. The Milky Way, our home galaxy, is a spiral galaxy typical of its class. It contains a central bar-shaped structure, spiral arms wound around this bar, and a halo of old stars and globular clusters extending far beyond the visible disk. The Sun orbits the galactic center at a distance of about 26,000 light-years, completing one orbit roughly every 230 million years. During the Sun's lifetime, it has completed about 20 orbits, meaning the solar system has traveled an immense distance through the galaxy, encountering different regions of the galactic disk and experiencing varying levels of radiation, stellar density, and spiral arm passages. These variations may have influenced the Earth's climate and biosphere, though the details are uncertain. The Milky Way is not isolated. It is part of a small group of galaxies called the Local Group, which contains about 80 galaxies, most of them small dwarfs. The two largest members are the Milky Way and the Andromeda Galaxy, with a third, the Triangulum Galaxy, being somewhat smaller. The Local Group is itself part of the Virgo supercluster, a larger structure containing thousands of galaxies. And the Virgo supercluster is part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies spread across 500 million light-years. Laniakea is not gravitationally bound. Its galaxies are being pulled apart by cosmic expansion. But within Laniakea, galaxies move under the influence of gravity, flowing toward a region of especially high density called the Great Attractor. The Milky Way, along with the rest of the Local Group, is moving toward the Great Attractor at hundreds of kilometers per second, part of a cosmic flow driven by the gravitational pull of unseen mass concentrations. This motion illustrates that the universe is dynamic on all scales. Even structures as large as superclusters are evolving, shaped by the same gravitational forces that govern the motions of planets and stars. The cosmic web, the filaments and voids, is not static but slowly evolving as matter continues to collapse into denser regions and voids continue to empty. Over time, This process will lead to greater segregation, with denser regions becoming denser still and voids becoming emptier. But the accelerating expansion driven by dark energy will eventually overcome this process, dispersing galaxy clusters and isolating galaxies beyond each other's horizons. The scale of the universe thus encompasses not only its current state, but also its history and its future. Understanding this scale requires integrating knowledge from multiple domains: observational astronomy, theoretical physics, cosmology, and even philosophy. It requires grappling with concepts that challenge intuition: the expansion of space, the warping of time, the existence of invisible components, the emergence of complexity from simplicity. It requires accepting that our knowledge is incomplete and provisional, subject to revision as new data and new ideas emerge. Webb's contribution to this endeavor is substantial but not final. It is one telescope operating for a finite duration, observing a finite number of targets. Future missions will surpass it, just as Webb surpassed Hubble and Hubble surpassed its predecessors. The quest to understand the true scale of the universe is not a project with a defined endpoint, but an ongoing exploration, driven by curiosity and the recognition that every answer opens new questions. This is the nature of science. It progresses not toward final answers, but toward deeper and more comprehensive understanding, always reaching toward the horizon of the unknown.